Thank you for coming, everybody. It's a great pleasure to be able to present something for you. I hope you'll find it interesting. Let's see if we can wake this up. There we go. So we'll be looking at how to deal with mutexes in complex scenarios, how it works in the real life, how to maybe arrange stuff so it becomes easier for you to do locking in bigger systems that isn't just a single thing. So this is based on a case from the real life. So I hope some of it can translate to some of the projects you're working on, or in future projects. It could be a tool in your toolbox. So first of all, I want to lead you to Roberto Clavi's talk yesterday on contention. It was really good, and it covers everything that this doesn't cover. So if you didn't see it, then find the video when it comes up. It's super good talk. I can highly recommend that. But yeah, let's look at the case we're looking at. So what we are working on is a database for ranking stuff. This is a project at my former workplace called Vivino, where we have a lot of stuff that we would like to have ranked in various ways. So Vivino is an app that allows you to scan wines and get information on the wine. That includes also how good does it rate compared to other wines and stuff like that. The old system that we were replacing was basically a cron job that ran every 24 hours or every week, depending on the data type. And we wanted to do this in real time. So we couldn't find any database that gave us any acceptable performance. Basically, it was either too slow at updating or requests were too slow because it had to do too much sorting at the end. So let's look at what we were dealing with, the data set. So there's 11 million different wines in the Vivino database. These we want to rank based on how people rate them and stuff like that. We want to rank them globally by country or by winery and by region and also by wine type. So already there we have quite a bit of different metrics for each type. We have 250 million vintages, which is the year of the wine. So each wine has 2016, 2015. We want these ranked by country, region, winery, and finally a single global list. Also, we rank users based on their interactivity with the app and how much they contribute to it. They're ranked by country, by region, and by wine style. So how much are you into a specific wine style? And we also keep a history of the user, so we can say, oh, you went up 5 spots in the rank from yesterday or something like that. So we looked at some designs. Basically, what we ended up with was a big sorted list, but a list that's split into what we call segments. So we have a list that's basically the top that has different segments that covers a range of a score given to a you or the wine or whatever we're dealing with. So this has a segment which covers from the maximum score possible to 1,000. The next covers from 99 to 100. These are the ranges of the scores. These are just numbers we assign, but for each segment we have some element which represents wines or users or whatever we're dealing with here. So it basically always covers the full possible score range. That's 64 bits in this case. But we also split and join different segments if they get too small or too big. Typically, we try to find a reasonable size for that just by experimenting. The most sensible part was around 2,000 elements in each segment. That's sort of the sweet spot. So there's a space, or there'll be a time when it says, oh, now there's too many in a single segment, so it splits it up. That's what's happening here. So we have a single segment with 200 elements. We split them up into two halves with 100 in each, and basically they cover a specific range in between. So this is then the elements have an index, so we can look up the user with ID this or the wine with ID that. That's a secondary index, so that also has to be kept. But it's actually the same structure as also. So as an example, we want to get the rank of an object with ID anything. First of all, some names. So a score is basically the sorted list of scores. So we have the highest scoring on the top, and basically sorted by that. We have index elements which are sorted by ID, so we can look up by ID. Sorry. First thing we do is we look up which list are we dealing with. We load the segments if they haven't been loaded already. We load the index elements for the element with this specific ID, the user ID or whatever we're looking for. We find out which segment does this refer to in the scores. We look it up, we load that segment, and we simply search through the list until we find the element or the user we are looking for. This also makes it free to get the neighbors, and how we calculate the rank is basically we take all of the segments above and we add that up, and the segment we're inside looking for, or looking inside, we take the offset in that, and then basically this user is number 120 in this list. Good. So, locking. Obviously, this requires some sort of locking. We would like it to be reasonably fine-grained, and we shouldn't, of course, keep it locked much longer than we absolutely want to. Of course, we would also like to be able to read from several parts of the list without locking the entire list. So, what options do we have? We have sync mutex. It's quite fast. You can't share it, so you only one Go routine or whatever can hold the lock. It's fair. I put that in quotes. Because when you request a log, you have the same chance of getting the log as everybody else. Also means there's no ordering, so even though you were the first one to request a log, you actually have no guarantee to get it before anyone else. There's no timeouts on this, and it's basically the same as having a channel with a spot for one element and just putting it in, pulling it out. Channels allows you to do timeouts, but that's about the only difference between those. And we have our V mutex, which has basically log unlock as the regular mutex for writing, and we have R log and R unlock. It's pretty fast. Again, see the talk I referenced yesterday on when to use it. There's still no timeouts. You have shared read access. And basically, there's similar to how you're not guaranteed to get it. If you request a write log, you are still contending with everybody, and you have an equal chance of getting the log you're requesting. And when you request a write log, you also block all incoming requests for read logs. It seems simple, but there's some caveats with that. Finally, you can also write your own. I heavily would not recommend that unless you really have some good reasons to do it. It makes your code quite hard for everybody else to read because you have to describe it and you have to basically make a contract with whoever is using your log. I would say sync atomic is kind of in the same category, and also is something you should only really begin using it if you really need to. So yeah, typical design. So what we have a list. We have some stuff inside the list we want to protect, so we add a mutex inside it, and that makes it pretty easy because hey, I know what that I just have to get a log before accessing anything in the list. Only problem is that you are basically creating a log that can block all access to the list and even parts of it below. So that may not be what you're looking for. Can then of course begin adding more complex stuff. So we say, okay, I have a log for the common stuff in the list, and then have some specialized logs for parts of the data. So whenever you're accessing scores or index, you have to get the specific logs for these two. So you can read stuff like ID of the list, everything else, without needing to log everything else out. And yeah, finally, you can also have, this is an update log. Basically, it's a log if you want a consistent view of the scores and indexes. And yeah, basically you make these contracts that okay, I will only get a write log if I actually am updating stuff inside the segments. So you kind of try to split it out to get more read logs and fewer write logs. So yeah, this goes deeper. Obviously, we're not at the bottom level. So each segment has a log of its own for updating total number of elements, stuff like that. And each segment, the elements inside that also has the own log. I'll not go into details with that because that's not really what we're looking at here. So, okay, we have an idea of what we want. So we list down the requirements we want. We want to be able to insert elements, update elements, delete elements, get rank of specific elements. We want to maybe get the 50% percentile of a list. We want to be able to, basically do some maintenance on the lists. And we begin working. Whew, it feels good to get some code done finally. So what we find is that we have a lot of these, okay, I need this type of log, and we defer the unlog. That's a pretty common pattern. I guess a lot of you who have dealt with logs have similar in your code. And also, we have like these comments. Hey, to call this function, you must have this logged already before you call me. And that's not really not what you want, because you're making it the problem of whoever is calling your function to make sure that everything is all right, and it's easy to make mistakes, and maybe you don't want to maybe the function you're calling doesn't actually need the log for the entire run, stuff like that. So let's see stuff like this. So we have, since we had the update log, if we require that, we have to log both of them. Then, we need to call this split function that requires the mutex to be unlocked. So we unlock, call the function, and then quickly log again, so the defer doesn't fail when we try to unlock it. And it doesn't feel right? So when we deploy, deadlocks. All kinds of small things, because in the end there was approximately 50 places that accessed these logs in various ways for reading or writing. So it was very hard to keep track of. First problem is that when you have two mutexes, you should always log and unlog in the same order. This is the other way around compared to the other one. So in the other one, we were grabbing the update log first and then the segments log, which actually means that if two are with the flip sign are trying to run concurrently, then one can get the segments log, the other can get the update log, and both are waiting for the other one to become available. So that's easy mistake to make. I don't like it when it's easy for me to make mistakes in my code. So we also have a second problem, and that is the side effect of when you request a read log. It will block if somebody else has requested a regular or a write log, and that's nicely documented. But actually, it's something that makes it quite hard when you have several layers, because one layer may be in the process of acquiring read logs, then a write comes in, and it can get down to the next level, try to get a write log, and then suddenly no read logs are being handed out anymore. So basically everything stops, and you got one of these nice deadlocks. So of course the thing you look into is, hey, let's try if we can hack this, let's fix the problems that we can see, but in reality that's not really what you should be going for. When you have a problem like this, and you can see it's already, I'm like a month into implementation, and this is already a mess, to be honest. So okay, let's see if we can find some way of working with this. So the first thing I tried was basically to wrap all the locking and unlocking into a single function on the list. Basically, you say, I want a read log, and I want an update log as booleans. Pretty nice. You get a function back that you can use to unlock whatever you got. That's actually quite neat, because you don't risk flipping them around, because you only got a single place where you do these locking and unlocking. Thing is, it doesn't tell you much about what's actually going on. So what we ended up with was basically a strut that contains the stuff we've locked. So it has these segments or pointers to the segments we are actually locking. We have an unlock function in there, and we can actually see if it was read-only or if it's logged for updates. And basically, we have two functions that return these things, so we can create a new. If we have an existing log, we can actually transfer that to the new. But also, if we want to load something, we basically, with the load flags, we can say I want a read only or something with an update log, and you get it back. So that actually makes it a bit more visible what you're trying to do. Also, anybody who has a valid, a non-nil pointer to this, unless somebody did something really silly, then you actually know it's been through one of these two functions to get the logs. Also, you can put in safety stuff, so calling unlock can also make sure you don't call unlock twice on the same stuff. You can print an error, you can panic, you can do what makes sense in your setup, and also set them to nil, so suddenly nobody will try to use an old segments that has been unlocked. So how would this look in real code? This is an example of I want to get an element at a specific offset in our list, or a number of elements. So basically, we have a public function that we can export that does the locking itself, and then calls an internal function that then accepts the logged segments and returns the results. Finally, if you have some some stuff you want to save, you can basically say, okay, update these segments on the list, and it will check. If you only required a read-only, then why are you asking me to update them? Because you probably did something wrong. So again, you can inspect how things are logged, because logs hides that information unless you, basically do some type checks or something like that. So yeah, limits the number of touching points on your mutexes. That's the best thing I can recommend about that. Have as few functions that actually does anything on your mutexes, because it basically reduces complexity to a more manageable level, and it allows you to share logged content between functions. You can also make it optional to, so if you send a nil value as the logged segment, it can load it. That's up to you. It can incorporate stuff like loading and caching automatically. So basically, as you request a logged segment, it will load it if it's not in memory, stuff like that. So yeah, that's thing is, you can also add more stuff to it without having to do major changes to your code. So yeah, another example is getting some specific elements in a list. So again, we reference which segment that we already logged. Do we have do these elements belong to? We have the elements themselves. We have which index in the list is it? Is it read-only? And we have the unlock function again. Again, you have some different load conditions. So you want some specific elements. You need to provide the index of the segment you want to load. But basically, it's pretty much the same. You have the replace segment when you've updated stuff, updated the total number of elements, and it will basically handle it for you. And you can also optionally make the replace segment unlock. That's again up to you. Generally, I wouldn't, because I think the one who requested the log should also be the one doing the unlocking. So maybe not have too much of that magic. So yeah, what does this not solve really? The nested locking is not solved by itself. You still need to make sure that your nesting is done in the correct order. So you don't acquire logs too early before you have the top level logs. But you can also prove that you have the log by the first argument ls proves that, hey, I have a logged segment for the level above. So that means it will only hand out logs to the level below if you actually have a log to the top level. That's a way of proving as you code that you actually have a log, and force yourself to do it correctly. So yeah, testing is really, really important for when you're dealing with mutexes, stuff like that, and because it's very easy to mess up. So what I've done is add a verify unlocked method on the list, which basically checks, okay, can I get all the logs within a specific timeout, something like that. And basically it allows you to have your tests where I create a new list, I put in some stuff, I check, okay, can I unlock everything because nothing else should be touching it? Can I do some operations, I split it, I verify it, and then I check again, can I get all the logs all the way down? That's really good for making sure that you can actually have some visibility whether your locking is working, because if you have a dangling lock, yeah, suddenly you'll get your test timing out, and you'll get some visibility on that. Thing is, though, if you have complex stuff, it can be any combination of two functions that create the deadlock. So I would recommend adding some complex stuff that just does a lot of concurrent operations. Maybe don't check the result. Maybe don't care about what actually ends up, but just run a lot. Check that you can get the logs when you're done with it. That's definitely a good thing to put in there. Okay. Back to the system. So I thought I'd put up some numbers. It's a couple of months old. So the system we ended up with is basically has these 700,000 lists of different ranked data. So we have had in one day in June or something, we had 33 million requests and average of 6.8. That's for getting an object with an element with a specific ID in multiple lists. The get around is for getting your rank and your friend's rank. So everybody you are friends with on Vivino, it sends in the IDs and get your rank relative to each other. That's a bit slower, 31 milliseconds. And then, of course, the updates. We don't prioritize updates that heavily, but they're not in any red area. So we have 2.7 million updates in a day for putting several elements into a single list. So typically, if a wine is updated, then all the vintages needs to be updated. Those get inserted in a bulk operation. We have the put a single object into multiple lists, and yeah, you can see it. The biggest list a couple of months ago, at least, was a list with 6 million elements, and it was split into 4,000 segments, and yeah, that's a big number of requests. And obviously, with the caching, you can insert. You definitely want to have such a big list in memory for this. So yeah, conclusion: you will make mistakes in concurrent programming. I'm sorry to tell you. I haven't met anyone who can just sit down and make everything completely correct. So make it easy for you to find these and also make it easy not to create them in the first place. So yeah, read-write logs can be surprisingly tricky. Remember that. And yeah, try to reduce your complexity, maybe by wrapping the logs similar to how it is here. So you basically have a separate object for your stuff where you have a log. That gives clear responsibility. So if I request the log, I should probably also be the one to unlog it. Make it testable, add easy tests, so you can check, okay, is there anything that could go wrong here? Hopefully that can also give you a bit more confidence in your concurrent code. But yeah, that's basically my advice to you if you are dealing with stuff like this. So I think we have some time for some questions, if there's anybody.
We have plenty of time for questions, and if anyone wants to, okay.
Hi, thank you very much for the great talk. One thing that does not concern concurrency, but I noticed it in the first slides you showed. You said that no database system worked for your use case. Yeah. Have you tried with the columnar database system like ClickHouse or maybe BigQuery or Redshift?
The thing is that they have a big input latency typically. So we didn't actually go too deep into that because but maybe there's some systems we didn't check, so we tried Cassandra and various SQL databases, stuff like that. We didn't find anything that was good enough for this specific use case, at least.
Thanks.
Okay.
Yeah, a question. What does it give when you test with minus res?
Sorry?
You have a res detector,
Yeah.
a runtime res detector, and was it able to detect some deadlocks? And
Yeah. So the question, is whether or how much you can use the race detector. Of course, I'd say, as a lot of other talks also say, always run your tests with the race detector. What can be hard is to detect a dangling lock somewhere. So if you run the test, but something is actually still logged after you run the test, the race detector will not find that. And sometimes your system can also be so complex that the race detector will not by itself detect a deadlock. Of course, your code will log up, but having checkpoints also makes it much easier for you to see this is the part that actually is leaking a lock or doesn't unlock properly or whatever is happening. So that's it can definitely help, and of course, if you have tests hanging, you know you have a deadlock. So you can find it that way as well.
okay.
Did you try out a design where you had one Go routine responsible for the database, and then have that receive requests from channels?
Yeah. So that is. That was actually quite a big consideration. We didn't try it out. Let's get that straight. The thing is, if you have a single Go routine that handles all operations, you have no concurrency on let's say a list or whatever, because that's the highest consistency level you want. So you want your scores and your indexes to be consistent. If you have everything coming in through channels, updates and requests, you get a strictly serialized operation, and that's nice because you get consistent results, and you don't need to concern yourself about deeper level logging. So it could definitely have been good. What we judged was that we had so many read operations that it was that we would see if we could get the benefit from having concurrent read operations operate on the lists instead. So yeah, it's definitely a neat design as well.
So thanks for the talk. And as far as I've understood, you have two different level of locking, because one locks for globally observable changes and one is granular for the single bit of data. Yeah. I was wondering if can you accept some latency in your updates to be visible to the rest of the state? Because in that case, you could remove some of the locking and do some copy on write. So have a warm copy that you write and a cold copy that you read. Yeah. And then you just switch over to them. Did you consider that design?
Yeah, it's actually the update lock. It's way back, I know, but it's actually meant to when you want a strictly consistent view of the database. So in this design, it's also okay if there's an update happening that you don't get a correct result for the specific part of the data you're working on, because it might be moving from one segment to another and it hasn't updated the index yet or something like that. In that case, if you want the consistent view, you grab the update log, which is just a per list mutex, no ifs and buts on that. So that allows you to get it strictly consistent. But for reads, we actually allowed things to not be completely synchronized, and occasionally, when data is being moved, you'll get a non-consistent result, and sometimes so that's an acceptable thing in this case, because for this specific system, it's okay that you don't always get the exact correct data.
So you gave some like latencies and pretty high like cache hit ratio. So did you like include those hits into the average or not? Like
yeah, the average is across all 700,000 lists. The big one, the global vintage, has so many reads that it never goes out of cache. It has an ARC cache, which basically keeps, once it's loaded, it pretty much stays there because it's accessed on basically every vintage you request. So that's why the cache hit ratio is so big for that. So you specify these number of elements you're allowed to keep in memory for frequently accessed lists. But yeah, to answer your question, the latency was across all 700,000.
Anyone else?
Good.
Okay, so thank you very much, Klaus, for the talk.
Thank you.